Here we are, the last big topic of chapter 14. That is titrations. Now, titrations are very, very common in chemistry. The basic idea of a titration is that you use a known solution with a known concentration of some reactant, and you use that known to discover the concentration of an unknown solution. So you use a known to find an unknown. That is the basic idea of a titration. And there are lots of different kinds of titrations. The main type is acid-base titration, but there are also such a thing as redox titrations. There's thermometric titrations. Really, pretty much any kind of reaction you can think of, there is a version of a titration for that kind of reaction. But the most common one that you'll see or come across is an acid-base titration, where you have some unknown acid or base, and you titrate it with a known base or acid, just depending on what you're looking at. So, the basic setup that we are going to be focusing on here, because like I said, there's variations on this, but the most common one that we're going to be looking at is having some unknown concentration of an acid in a beaker. So we have some solution down here. We know it's an acid, but we don't know what its concentration is, and we're going to drop into that beaker of unknown acid a known concentration of a base. So you might say that we chemists drop the base. I'd just like to apologize for that. I had to do it. It's in my contract. I have to make at least one really terrible chemistry pun every chapter. So now that's done with, let's move on here. So, in an acid-base titration, a solution of unknown concentration, which we call the titrant, is slowly added to a solution of known concentration from a burette until the reaction is complete. And actually, usually, you can do titrations that way. The way that is phrased, it seems like it's saying that the unknown is in the burette. Usually the unknown is in the beaker, but you could technically do it the other way around. It'll work either direction as long as you have a known and an unknown. But we are going to always have the known in the burette and the unknown in the beaker. So when the reaction is complete, we've reached what we call the end point of the titration. Now, determining when that end point happens can sometimes be a little tricky. It just depends on the reaction. Usually, we're going to have some kind of an indicator that tells us when we've reached the end point. These usually have a color change that happens at the end point. The most common one is phenolphthalein. It usually changes color, well, not usually, it does change color at right around 8. A pH of 8, which is close enough to 7 that we kind of call it good. We say, okay, if we're trying to find the end of the titration is at 7. The fact that it turns pink at around 8, that's close enough that we can go ahead and call it good. So that end point is also sometimes called the equivalence point. So end point and equivalence point here, they mean the same thing. This is the point where we have put in as much acid or as much base, just depending on what we're adding and what we're starting with. We have equal amounts of both acid and base. So if we have an unknown acid in the beaker and we're dripping a known base into the beaker, the equivalence point is when we've added exactly the same number of moles of hydroxide as we had hydronium ion in the solution to start with. So that would look something like this if we had a strong acid and a strong base that we were titrating. So we have our unknown acid down here, it starts out clear. We have phenolphthalein in here. Phenolphthalein, if it's in the acidic range of pH, it is clear. As we start to add in the base, the OH- ions, the hydroxide ions, start to react with the H+ in solution to just form more water, is what it would make. Because again, we just have strong acid and base here. We don't have any weak acid or weak base to have a conjugate. It would just form water. And so as we start to change all this H+ into water, we start to see some pink showing up in the solution. Now usually when we do these titrations, the pink will show up right away, right when the drop of base hits the solution. That's because immediately when that drop hits the liquid, right where the drop hit is more basic than acidic. But then very quickly, within a second or so, that drop of base gets distributed out to the whole solution. It's not just concentrated right where the drop fell. And so it goes back to being clear again. But you can usually see a little burst of pink even right at the beginning of a titration when that drop hits the liquid. Now what happens is as we get closer and closer to the equivalence point, that burst of pink stays longer and longer. It takes a longer time for it to go away because we're getting closer to that end point and there's not as much H+ to use up the base. And so the end point, or equivalence point, is where we see that pink color not go away. Now this dark of a pink is actually darker than we would usually want. We want the lightest pink possible when we're doing titrations with phenolphthalein, because that means we're as close to 7, as close to the pH of 7 as possible. This is probably something around 9.5 to 10. That's probably what the pH of that solution is, because it's a fairly deep pink. All right. So if we're plotting what's happening in these titrations, usually what we're going to plot is the pH of the solution versus the amount of titrant that we've added. So the amount of stuff that we drip in, the amount of the known that we drip in. That's what we're going to plot. So it's the pH versus the amount of the known stuff that we drip in. So the inflection point in the curve that we find here, because what's going to end up happening, and we'll see some graphs here in just a second, if we start with an acid, so we have pH over here, mils of the titrant over here, we're going to start pretty low on the pH, and then as we start to put in more and more of that titrant, we're going to have a pretty steep increase in the pH right around the end point, and then it'll level off again. And we'll talk about why it has this kind of strange shape here when we a few slides from now we'll talk about that. But all titrations are going to have roughly this shape. Now if we're doing the opposite process where we start with a base and we titrate it with an acid, it's just going to look essentially flipped. It's going to be the mirror image of this one, but the overall shape stays the same. So the equivalence point pH is going to vary based on what it is that we're titrating. If we have only strong stuff, so if we're titrating a strong acid with a strong base, then there's no weak acids or bases involved, and so when all of the neutralization is done, all we're left with is neutral salts, like a sodium chloride, for example. So if we were titrating HCl, which is a strong acid, with sodium hydroxide, which is a strong base, the hydrogen and OH- would make water, and we'd just be left with NaCl. And that is a neutral salt. It's not going to have an effect on the pH, and so the equivalence point will have a pH of 7. So we would have right here, if this was a strong and strong titration, it would be right there is a pH of 7. Now if on the other hand we are using either a weak acid or a weak base. So if, for example, we were titrating ammonia, when we titrate this with a strong acid, we turn this into ammonium. And ammonium is a weak acid. So even when we've neutralized all of the ammonia, what we've done is we've made a new thing that has an effect on the pH. So if we have a weak acid or weak base involved in our titration, the equivalence point pH is not going to be 7. It's going to be above or below 7, just depending on what weak thing we started with and the weak thing that we made as a result of our chemical reaction. So here's one of those graphs I was telling you about. So we have our strong base being added to a strong acid. So the equivalence point, which is the inflection point here, for those calculus fans out there in the group, this is where the, make sure I get this right, this is where the sign of the first derivative of the curve goes from being positive to negative. So up to this point, the first derivative of the function that describes this curve was positive. So the slope was increasing, 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 and then at this point, the slope begins to decrease. Now, the graph is still going up, but it's not going up as fast. And so that means that that first derivative has gone negative. And so this equivalence point is always going to be the same in terms of the mathematics of it. That's always going to be the same no matter what we're dealing with. It's just the pH that will be different. And so this one is directly at 7 because we have a strong acid and strong base. So if we were doing the opposite, so if we started with a base and we titrated with an acid, just like what I attempted to draw earlier, we would just flip that. So we just get the mirror image of what we had before. Okay. I think I'm actually going to go ahead and stop this video here, because if I get into titrating a weak acid with a strong base, it's going to take me a while to get through this, and so I don't want to have it as like the second half of a video, because then the video will be 30 minutes long. So we'll go ahead and stop it here, and in the next video we are going to talk about the more complicated case of titrating a weak acid with a strong base, and how we find the pH at different points along the curve. Because in a strong acid and strong base situation, it's just really simple. It's just how much base or acid did you start with, how much has been neutralized, calculate the difference, and then plug that into the pH equation. Because it's all strong stuff, there's nothing involving an equilibrium with a strong acid and strong base. But with weak acids, we are going to worry about equilibria. And so we'll talk about that in the next video.